Hello and welcome to the University of Salford's School of Science, Engineering and Environment Postgraduate Research Seminar Series. Now, we lost a little bit at the beginning of this one, but hopefully there's plenty for you to get your teeth sunk into. Hope you enjoy it.
Volume or pressure, volume and temperature for fluids, how they squat when you compress them or expand when you heat them. And surprisingly, it's much harder to do this than you would think. So why does this matter? Well, we see hot fluids in planetary interiors. There's a cross section through Uranus and Neptune, and just the bottom of the outer layers, you're up to 100,000 atmospheres pressure, or then in 2000 Kelvin. These are figures from the part my colleague Helen Maynard Casely wrote to go in my textbook on liquids and supercritical fluids. And so at modest pressures, we can use piston and cylinder devices to directly measure the volume of the fluid as we compress and heat it. But for really extreme pressures, the only option is a device called the diamond anvil high pressure cell. And in this device, so the piston and cylinder are still a part of the device, but the whole thing's about the size of this pointer. Okay. And actual compression takes place between tips of a diamond, one diamond on top of the piston and the other inside the cylinder. And then between the diamonds, there's a gasket and the hole in the gasket containing the sample. And the smaller you make the tips of the diamonds, the higher the pressure you get, a bit like the elephant and the high heels on the previous slide. Okay. And so typically we might use diamonds with 300 micron diameter coolants. These tips are 300 microns across and get to pressures of up to about 1 million atmospheres. So it's worthwhile to remember what those dimensions are for later. So typically it's 300 to 500 microns for the tip of the diamond, and maybe 100 for the thick. And because the diamond is transparent, you can just look in through the diamond to visually see the sample in a microscope. And that's what this image is here. And so for solids, it is, relatively speaking, straightforward to measure the equation of state in diamond anvil cell. This figures the work I was doing at Diamond Light Source in Oxford a couple of years ago. So you see for X-ray diffraction. This is one of my high pressure cells on the beam light diamond light source here. And Bragg's law, in very level physics, to work out the volume versus pressure relationship from the X-ray diffraction. And you get these narrow X-ray diffraction peaks, which you accurately fit to work out lattice constants and volume. So for solids, it's pretty simple. But of course, for fluids, there's not the long-range order that permits this approach to be taken. Okay. And so to date, no one has done succeeded at measuring an accurate equation of state of a hot fluid in the diamond anvil cell. Okay. About 20 years ago, researchers in France came up with a novel solution to the problem of fluid equation state measure in diamond anvil cells. So rather than trying to use X-ray to measure the distance between the atoms, they just measured the entire sample chamber volume by diffracting visible light. Okay. And so they did at room temperature, so the volume versus pressure equation of state for helium and a few other simple fluids as well. And over the past 2 years, we've been reproducing their experimental method here at Salford and working out why other people, not least research themselves, didn't follow in their footsteps and make this big scientific field. So the simple parts are, we can take a photograph of our sample chamber and count the pixels using software to get the cross section. And then there's the thickness. We can shine white light through the sample chamber. So that's basically shining it in this direction through the diamond. And at certain wavelengths, when you plot the intensity versus wavelength, certain wavelengths there, these peaks where light was bounced back and forth a few times across the sample chamber is in phase with light's gone straight through. And if you put these wavelengths into an equation, what you get is the thickness times the refractive index of the sample. So n is the refractive index, T is the thickness. Okay. And a couple of years ago, we had a graduate project working on this, and this basically, as far as we got now, worked 2 years ago. So we looked at the various potentials for errors in this process, and so Kevin, the student, deliberately messed up the fitting of these peaks, tried the wrong fitting function, got the background a bit off deliberately, that kind of stuff. And it's remarkable how robust the finding for this product NT is against these arbitrary choices or errors. And so the hard part is separating out the thickness from the refractive index. And so the works in France 20 years ago did manage to do this, and we reproduced that and identified the products. So the way they did this is that it's voiced about in diamond amber cell, the surface of the diamonds, two diamonds, are very close to being parallel. So you've got, flip back a few slides, these two parallel surfaces here. Okay. And so the diamond amber cell can't like a device called the Krpetic echelon. This image of an echelon from Wikipedia has these two flat plates. And so comparing to what we're doing, that's where the sample goes between diamond coolants. And when you shine monochromatic light from the laser, usually through a sample, at certain scattering angles, the light's bounced back and forth a few times is in phase with light's gone straight through. And that leads to these rings appear if you have a screen or camera down here. And so we can observe this phenomenon, and how does it help? So when we do this experiment, light goes in and out the cell via a path like this through the diamonds. And so the actual scattering angles we observe depend, amongst other things, on the diffraction due to Snell's law at these interfaces, diamond sample interface, diamond air interface. And Snell's law is here, also from A-level physics. Okay. And so when we put together the equation to give the scattering angle in terms of various different variables, the refractive index comes into it by Snell's law, which is not multiplied by the sample thickness. Well, the change of scattering angles here just depends on the two refractive indices, not how wide this distance is. And so that's the information that allows you to separate out the refractive index from the thickness. But when we did this, we found how rings were very poor quality. So we compared those to those rings from a purpose designed echelon. Okay. And so that could have been because these do better at how we collect and focus light and filtered out other stray beams, or it could be because diamond surfaces weren't parallel enough. Now in the lab, we have quite a few diamond amber cells. This is most of them sat on this table here. And we've noticed that the quality of rings did vary a bit depending on which cell you were using. It made us think that the problem with diamond surfaces were not parallel enough. And the solution to this lies in my friend, colleague, and mentor, David Dunstan, who just retired as a professor of physics at Cornell University. Now, in the 80s, he designed a diamond amber cell in which you could tilt one of the diamond surfaces to make them more parallel. And his innovation was ensuring that, to first order at least, the massive force you put on the diamonds isn't transmitted through the delicate tilt mechanism. Now he designs for completely different reasons, but nonetheless is what I needed. Now the problem with his cell is it is absolutely tiny. He designed it to fit inside a cryostat, so this cross section here is about the size of a 1 penny piece. And for that reason, his cell arguably doesn't work very well, at least it's very hard to use. So what I did is I designed a different cell, which followed the same principles as his cell, but was a bit bigger, and therefore more accurate and easy to use. And my colleague for the workshop built it. I don't have a photo of him, but he can do things which seem like magic to the rest of us. So, and this gives a massive improvement in the quality of the rings. So comparing these photos, I've had to zoom out massively in that photo to get all the rings that we got with this new down cell with a tilting diamond. So that the entirety of that photo is like this part, the second photo with it. But all that did, I feel, is reveal what the real problem was. Because to get this to work, Michael had to go for precision of engineering types of fit that was absolutely incompatible with experiments at high temperature. So when you got everything fit together so snugly, it only takes a slight difference in thermal expansion from different parts of the cell. Stuff that's meant to move to stop moving, or stuff that's not meant to move to start moving. And so there's no way to do experiments above room temperature with this kind of device. And why it's important? Well, this graph, we've got temperature on the x-axis and pressure on the y-axis, is basically all the measurements made of the methane equator state using piston cylinder devices. And you see at room temperature, we can nearly get to freezing with the piston cylinder device. But at high temperature, extrapolate up here, we're absolutely nowhere near. So it's at high temperature, the real work is there to be done using this method, especially because that's a log axis as well. And so we now have a different solution, which we think no one's thought of because it's too simple. So we will focus laser into the down cell. And when your sample chamber is sort of 50 or 100 microns thick, you can see, if you set your optics carefully, you move the cell towards the lens, it focuses on the first diamond, move a bit further, focus on the second diamond. And with the micrometer accurate to 1 micron, you can measure this movement accurately enough. Now, of course, the refraction at the surface diamond still comes into the equation when laser beam comes in through the two interfaces, but in small angle approximation, you get quite neat equations. And so we want to measure the thickness, and it's nice to measure the factor of index 2. And the parameters delta and T prime, what we measure to use the white light fringes and by moving the cell. So everything is ready to actually do the first ever direct equator state method to the hot fluid. Made our first attempt on 2nd of August, my birthday, and had 0 data points. The second attempt last month, and we got 2 data points. We're getting there. We have had a lot of control experiments at room temperature. So salt is great for this because salt's transparent, and so you can measure the process using this method. It's a solid, so it's been measured very accurately using X-ray diffraction, and it's also much less compressible than our fluids. So it provides very rigorous test by experimental methods. That's how far we are now, and I think I've managed time as well. So, acknowledgements and any questions.